Okay, now we're going. Number 53. Okay, let's see if that's one of the ones. All right, number 53. So homework 3-4. Are you sure that was one we were supposed to do?
We have section 47 through 73 odd.
What did I do? Looks like I skipped that. Oh, okay. That's interesting. Let's see what we got for 53.
That was the only
Okay,
problem. That was the only problem in that section you skipped.
53. Where are we? Sine 2x, cosine 2x.
Yeah, it should be fairly straightforward, but I'm not sure how they simplified it again.
Okay, so now I got it written down now. So, number 53. And we have f of x equals sine 2x cosine 2x. Okay, so this is what? Going to be, when we do a derivative here, it's going to be a product rule, right? So the first times the derivative of the second chain rule. I'm going to use the second line here so we don't have to stretch this out too far. So that's the first times the derivative of the second plus the second times the derivative of the first chain rule. Okay, so what do we got? In the beginning, we have what? We've got a negative sine squared of 2x times 2. So let's put that 2 out in front. And then for the second part, we've got the cosine, we've got 2 times the cosine squared of 2x.
That's what I currently have right now, is exactly what you have written there.
Okay, well, that's good. Now, they might have factored a 2 out. I don't know. They might have done this.
The only thing is, can you not use the Pythagorean identity there because the one's negative?
Yeah, I can't use an identity because that's correct.
Okay.
So I don't know. Did they have did they have that line?
I mean, they only give me the answer, and the answer was 2 times the cosine of 4x. Yeah.
Oh, is that a double angle?
Oh.
Oh, I gotta think about that. I don't know. I'll tell you what. Uh, I'll check on that. No, we'll talk about it. We'll talk about it tomorrow. But that certainly looks correct to me.
Okay, that's fine then.
Okay. Welcome, Maria. So, so some of you started the assignment. Do you have questions you'd like to bring up?
61.
All right. Let's see if I did that one. So there's 61. 1/4 times the sine squared of 2 theta And I just rewrote, the meaning of that sine squared is written to the right here, equals 1/4 the sine of 2 theta quantity squared. Okay, so just setting that straight. So when you take the derivative, you can leave the constant out there. Do the power rule. Bring the power down. 2 times the sine of 2 theta. Now, the sine of 2 theta is the derivative. The chain rule says that's the cosine of 2 theta. And the chain rule again says, what's the derivative of 2 theta? 2. Okay, so all these things are being multiplied. 2 times 2 times 1/4 is 1. So there's no number here. And you've got the sine of 2 theta, cosine of 2 theta.
The answer in the back of the book had like half sine of 4 theta.
Half sine of 4 theta.
Yeah.
Okay. Did you have this?
Yeah, my answer is
what
what you had.
Okay. I'm going to have to look that one up too. This certainly looks correct to me. They might have used a double angle theorem or something to go further, but I would be happy with this answer.
Okay.
So Travis, yours was what, 53?
Yeah.
And this is, so I'm going to have to look those two up in the book. I'll do that for tomorrow again. This certainly looks correct to me. Anybody else question out there? All right, so what we're gonna do, like I was telling Travis earlier, there's a couple things I never got to, we need more time for. We're gonna go through those, and then we're gonna just do a bunch of examples today. And then hopefully that'll get us more comfortable with this whole thing. So I believe I showed you this one in class last time. These repeated application of the chain rule problems are kind of, you got to really keep your concentration and keep asking yourself, is there another inner function? Is there another inner function? So on this one, you've got the sine cubed of 4t, which really means the sine of 4t cubed. So we start with the power rule, 3 times that quantity to the second power. But then because of the power rule, I need to take the derivative of the sine of 4t, which is the cosine of 4t. Oh, and there's another interior function, 4t. So I got to take, finally you're down. So you're finally down to this right here where you have, we've done the chain rule twice, and then just bring it all together by, this stuff's all multiplied. So 3 times 4 is 12. And then go back to the shortcut notation, sine squared 4t, cosine 4t. So just wanted to remind you guys, I don't know if, I think I showed this, we were on this slide last time. All right. So, have I showed this to you last time?
Yeah, I believe so.
Okay. Yeah, that's right. We did do this. So this is very important. The derivative of the natural log of x is 1 over x. And of course, if x is an inner function, the number 2 says, don't forget, you got to use the chain rule if that's more than just an x. So if it was like the natural log of 2x, we would do 1 over 2x, but then we'd have to differentiate the 2x in the chain rule. Okay. This I didn't show you. Let's just take a look at this. This is actually a proof of the derivative of the natural log is 1 over x. So let's start at the top. We have the original function, y equals the natural log of x. Isn't this the same thing? Because the natural log of something means e to that power is x. So to go from 1 to 2, I mean, that's the meaning of the natural log. All right, so let's take the derivative of both sides. The derivative of e to the y power and the derivative of x. Well, what's the derivative of e to the y? Well, it's itself, but we don't know. Y might be a function itself, so we got to use the chain rule, dy dx. And on the right, the derivative of x is 1. And if we divide both sides by e to the y, we get 1 over e. The derivative of y with respect to x is 1 over e to the y. And what's e to the y? If you look up on top here, it's x. So a little bit of a trick there. But anyway, let's we don't usually look at proofs, but there we're going to look at a proof for why the derivative of the natural log of x is 1 over x. Okay, so let's do a natural log problem. Sorry, this is marked up, but so the problem, oh, it's ironic. I picked that exact problem that I was talking about a few minutes ago, the natural log of 2x. So we begin by taking 1 over 2x. Yeah, this is where my markings make more sense. So look over here on the right. So the derivative of the natural log of something is 1 over that thing. So that's this part right here, 1 over 2x. And then, of course, what's 2x? That's a chain rule. The derivative of 2x, 2. And then, of course, you do a little simplification. That one also turns out to be 1 over x. Look at b, the natural log of x squared plus 1. Start off by putting 1 over that thing, 1 over 2x squared plus 1. Chain rule, the derivative of x squared plus 1, 2x. Okay, that one I can't cancel on. And the answer we just write is 2x over x squared plus 1, like it shows over here on the left. Part C, we have x times the natural log of x. Well, that's a product rule. Okay, so we take x, the first, times the derivative of the second, plus the second times the derivative of the first. Well, in this first one here, the derivative of natural log of x is 1 over x, so we have x times 1 over x. And then the second part, the derivative of x is 1. And so I think you can see that we wind up down here, simplified version is 1 plus the natural log of x. Another example, D. What's the natural log of x quantity cubed? What's the derivative of that? Well, first we have the power rule, 3 times the natural log of x squared, power rule. But then we chain rule, what's the derivative of the natural log of x? 1 over x. And this is kind of an odd way to write it. I would write it as 3 times the natural log of x quantity squared over x. But anyway. Okay, so we're just applying, how does one take the derivative of a natural log? Okay, so it's 1 over the thing you're taking the natural log of, and then if there's a chain rule, make sure you apply it. So now, do you guys remember your log laws? The log of a so here we have this, the function is the natural log of x, square root of x plus 1. How do you take the natural log of the square root? Well, you can think of that as x plus 1 to the 1/2 power. And what's the natural log of something to a power? It's that power times the natural log of the base. So here, we're right here in this underlining section here. The natural log of x plus 1 to the 1/2, it's equal, so with log laws, it's 1/2 times the natural log of the base, x plus 1. And what's the natural log of x plus 1? 1 over x plus 1. And then do we have a chain rule? What's the derivative of x plus 1?
1.
Yeah, so that's why it doesn't show up. But so we got the 1/2 from the power. Then we've got the natural log of something. The derivative of the natural log is 1 over that thing. And chain rule, in this case, turns out to be 1. So we're done. So what made this easier is we didn't have to do the derivative of a square root because of the laws of logarithms. The logarithm of a square root is 1/2 times the logarithm of the thing under the square root. So here, the log laws really help you quite a bit here. Here's another example of log laws helping us out. So we've got this rather messy fraction here, the natural log of x times the quantity x squared plus 1 squared divided by the square root of 2x cubed minus 1. Well, what do the log laws say about that? If we're taking the natural log of that, well, a product, well, first of all, we got a power here. That's the power times natural log of the base. And when we have a product, that's the sum of the natural logs. And when you have a quotient dividing, that's just subtract. So, so once again, on top, you got the natural log of x plus 2 times the natural log of x squared plus 1 minus 1/2, because this is a square root, 1/2 times the natural log of 2x cubed minus 1. Now, we haven't done a derivative yet. All we did was use log laws. Now, let's take the derivative. What's the derivative of the natural log of x? 1 over x. Plus 2 times the natural log of x squared plus 1. So we put the x squared plus 1 on the bottom. Chain rule times 2x. That's where that numerator comes from. Minus 1/2. Natural log of 2x cubed minus 1. That means 2x cubed minus 1 is on the bottom. Chain rule, 6x squared. And that's why that winds up on the top. And then it's just a matter of algebra from there on in. These 2's, the 2 times 2x can be written as 4x on top. Here we have 1/2 times 6x squared. That's 3x squared. And they didn't bother getting these 3 fractions together, which I'm happy they didn't. So when you're taking the natural log of an expression, use your log laws to get it written in a nice addition subtraction line like we have right here. This red, yeah, this equals line here. And then go ahead and do your derivative. Okay. This is not a derivative. This is just okay, so what happens when you take the natural log of something to a different, not the natural log, excuse me, the log to a different base, not e, not a natural log, but any base, a. And it's, you know, they could have, I almost wish they'd have written this a little differently. They could have said the natural log of x over the natural log of a. That's really what this thing says there. So that's not a derivative. That's just a statement about logs. Okay, so that comes in handy. Now, yeah, I got to go here. Oh, we messed that up. Okay, I got to go back here. Yeah, excuse me a second while I get this bigger. I had it all set to go, but then they asked a question. And all right, so this box right here, this is from page 158 in your books. So it's these 4 things right here: derivatives for bases other than e. So you already know how to do base e. That's a natural log. So this one, notice the base is a number 1 here. The base is a. So how do you take the derivative of any base a to the x? And the answer is it's itself, a to the x, multiplied by the natural log of its base. So I know that's not, they wrote the a to the x on the end, but it doesn't matter. So what's the derivative of any number to the, any constant to the x power, no matter what the base, it's itself, just like e to the x, you know, what's the derivative of e to the x? Itself. What's the derivative of a to the x? Itself times the natural log of its base. And by the way, that, here, look at it. Here it is again. What's the derivative of any letter to the x power? Itself, here you can see I wrote that, times the natural log of its base. And this works with e to the x. Look, what's the derivative of e to the x? Itself times the natural log of its base. What's the natural log of e? 1. Oh, that's why the derivative of e to the x is e to the x. Because the derivative of, you know, because the natural log of e is 1. So this is actually, in a way, showing you why that beautiful derivative exists. Okay, so the derivative of any base to the x power is itself multiplied by the natural log of its base. And now you can see why the derivative of e to the x is just e to the x, because the natural log of its base is 1. And so e, you know, the answer is e to the x. So, all right. So here's another natural log. Well, we have some different bases here. Okay, so here we go again. What's the derivative of 2 to the x? Itself times the natural log of its base. So 2 to the x times the natural log of 2. What do you do with part B? What's the derivative of 2 to the 3x power? Itself, 2 to the 3x, times the natural log of its base. And then we have a chain rule because the inner function there is 3x. So put that all together, get your answer over here on the right. How about C? Log base 10 of the cosine of x. Well, I don't know if I showed that to you, but let's go back and look here. Yeah, that's this number 3 here. Number 3 in this list. What's the derivative of the log base, any base, a of x? It's 1 over x, just like it was when it was a natural log, but the difference is in the denominator, you notice we also multiplied by the natural log of the base. Okay, so let's see, if I put that off to the side. So in other words, let me just write a little bit here. So if f of x equals the log base a of x, the derivative of that is 1 over x, but in the denominator we also have the natural log of a. So you can see that when you do the derivative of the natural log of x, well, what does that mean? That means, basically, that means the log base e of x. That these are the same thing. And if you follow the rule up there, the answer is 1 over x times the natural log of e. And what's the natural log of e? So when we learned that the derivative of the natural log is 1 over x, we were, again, learning a special case because of its special characteristic that the natural log of e is 1. So this is the more general case. What do you do with any log base? Base 3, base 7, base 2.4, doesn't matter. It's 1 over that thing, and in the denominator, you have to put the natural log of whatever that base was. Okay, so now we can go back and do this part C problem here. The log base 10 is 1 over the thing we're taking the natural log base 10 of, 1 over cosine x times the natural log of its base in the denominator, natural log of 10. And then we have a chain rule. The derivative of the cosine minus the sine. So that's where that numerator comes from. And of course, the sine over the cosine is a tangent. That's where they got the tangent from here, and it's negative. So they put a negative on it. D, it says after rewriting the function below using logarithmic properties, then go ahead and find the derivative. Okay, so first, the log base 3 of the square root of x over x plus 5 equals, all right, 1/2 times the log base 3 of x, right? This is really x to the 1/2 up here, and the rule for taking a log of something to a power is take the power times the log of the base. So that's why that's there. Minus, because it's division. And on the bottom, the log base 3 of x plus 5. So now it's time to do, so we haven't done any derivatives yet. Now let's take the derivative of this whole thing. So you can take the derivative of each part. What's the derivative of 1/2? Log base 3 of x. Well, you got your 1/2. Leave the constant there. 1 over x times the natural log of the base, 3. Second part, same thing. 1 over x plus 5 times the natural, on the bottom, you got to put the natural log of that base, 3. And then they just got a common denominator. Brought it together. And if you want, I can show you that. But that's more of an, so I'm not, this is more of an algebra solution from those two, but the meat of it is right here. Okay. So now there's this page in the book. You'll see they've got a summary of all the derivatives that we have learned so far. Okay. Let's just go through them real briefly. It's not like we're all done, but so far, what do we know? So we know that up here, the derivative of a constant, that's 0. Then we got the power rule. The derivative of x is 1. Yep. Then we got the constant multiple rule, which says, hey, if you got a constant out in front, you can basically ignore it. Just do the derivative of the rest of it. We learned that when you take the derivative of a sum or derivative of a difference, you can just take the individual derivatives and then add them or subtract them. So no surprise there. My apologies. Too much talking. So then we learned the product rule and the quotient rule. And then we spent what? We're still on it, but we're doing the chain rule. The chain rule gave us the general power rule. All that is the power rule with the chain rule. We've learned some trig. We actually only learned the first two. The derivative of the sine is the cosine, and the derivative of the cosine is minus the sine. And these other 4, remember, we developed using what? The quotient rule. And finally, the ones we added today are the derivative. Well, we added this some days before. The derivative of e to the x is e to the x. Today we learned that the derivative of the natural log of x is 1 over x. And we learned that the derivative of any base to the x is equal to itself multiplied by the natural log of its base. And then if you take the derivative of any of the log of any base of x, it's 1 over x again, but you do have to multiply it by the natural log of its base. So there's a summary, and you wanna really get very familiar, almost have those. You really have to have this. You got to have this memorized. So now I want to do some problems with you. Does anybody have any questions? So we want to do some 3.4 problems, examples, and that's what we're going to do. So the first one I picked out is number 17. This is pretty straightforward. So what did I use here? What general rule that we have learned did I use in this problem?
Quotient rule.
Yep. And does everybody see how I did that?
Yeah.
Okay, no problem. Number 23. So what do we use here? Well, it's going to be the product rule, right? So I would start off by saying the first, x squared, times the derivative of the second, 4 times x minus 2 to the third. Chain rule, I know I could have forgotten it here and gotten away with it, but it's the derivative of x minus 2, which happens to be a 1. Okay, plus the second times the derivative of the first. And then, okay, so that's the same thing, only just kneading it up, you know, putting things in a little different order. Okay, here's the part that maybe might take a little explanation. Factoring. What's in common between these two terms here? Well, for 4x squared and 2x, you could take a 2x out of that. And for x minus 2 cubed and x minus 2 to the fourth, I could take out the lower of those two, x minus 2 cubed. What's left in this 4x squared x minus 2 cubed term? The x minus 2 cubed is all out, just a 2x, right? And for the second term, the only thing left, the 2x is gone completely. I just need one more. I need to take this times x minus 2. And then simplify the brackets. And you're done. Any questions on that one? Okay, let's go to the next. Number 30. So here I did a little algebra before we did the derivative. So I saved myself from that outer power rule, you know. So I just squared everything. Okay. Now what? Quotient rule time. So denominator times derivative of numerator minus numerator times derivative of denominator. Don't forget that quotient, that chain rule there. So after you do your power rule for the derivative of the denominator, you also have to do the chain rule, and of course that's over the denominator squared. Okay, next, now I just rewrote it a little bit. I really didn't do it. I just, you know, took 3t squared times 2t to the fourth. And then, okay, let's see what happened here. So here we go with factoring again. Term 1, term 2 of the numerator. For 4t cubed and negative 6t to the 6th, I can take out a 2t cubed. For t cubed plus 2 to the second, t cubed plus 2 to the first, I can take out a t cubed plus 2 to the first. What's left in the first term? 2 and 1 t cubed plus 2 term. On the other end, we got a 3 left and a t cubed, and there's nothing left from the t cubed plus 2. Bring the parentheses together. Yeah, either one of those circled ones. What happens is, do you see how one of those t cubed plus 2's, that's this one right here, canceled with one on the bottom? So I was able to cancel that t cubed plus 2 with one of the 4 t cubed plus 2 terms on the bottom. And you could have it either one of these two circle ways would be just fine. Questions or comments? Okay. Yeah, number 50. So secant of x squared, and that's this is not secant. Yeah, this is not this thing in red here, secant squared of x. This is secant of x squared. So that's why I made it a little clearer, I think, by putting parentheses around it. What's the derivative of the secant? This is one we developed in class. It's the secant of that thing times the tangent of that thing. So secant x squared, tangent x squared. And then there's a chain rule, x squared, the inner function, the derivative of that is 2x. You could write the 2x in the front, but basically that's that's it. Speak up if you have any questions or comments. Okay, let's take a look at number 60. So we got the cosine squared of 8 theta. So just because of this shortcut notation, I made it. I think it makes it clear that these mean the same thing. But this is clear for doing a derivative, isn't it? Yeah, because the first thing we're going to do is the power rule. We're going to bring the 2 down, multiply it by the cosine of 8 theta to the first power, and then we're going to do the chain rule, because the derivative of the cosine is minus the sine of that angle. And then we're going to do the chain rule again, because 8 theta is also a function. So then, just overall simplification, 8 times 2, and we got a negative, so I threw the negative out in front. Comments or questions? All right. 68, another trig problem, but this is okay, we got all kinds of things going on, right? We got a square root, we got some trig, we got a pi x in there. All right, so the first thing is, I didn't do anything there. Does this make sense that you could rewrite it this way? That square root can be written as that thing to the 1/2 power. So just a clarification. So derivative. So first of all, the outer thing we're doing is cosine, and the derivative of the cosine is minus the sine. So minus the sine of that whole thing. Chain rule. The derivative of, so now we're in the inside. The derivative of the sine of something. Oh, now the next thing we got is the 1/2 power. Yeah, The next most outer thing is to the half. So we do the power rule. 1/2 comes down, multiplied by that same base, reduce the power by 1. Now, we've got this blue sign underlined thing, and that's the cosine of tangent pi x. But we're not done yet, because the derivative of the tangent of pi x is the secant squared of pi x. And we're still not done, because the derivative of pi x is pi. So this is like the chain rule bonanza here. We had to use the chain rule how many times? I don't know, 4 times, I think. Yep. And I mean, there's a whole lot you can do to simplify that, but I mean, yeah, we could get rid of the negative 1/2 power and bring it on the bottom, but more important is that you get that the chain rule had to be used repeatedly here. All right. (72) x squared times e to the minus x, excuse me. So this is what? Product rule on the outside. So the first times the derivative of the second. Notice the chain rule there? What's the derivative of e to the negative x? Well, it's itself, but there's an inner function, negative 1 times x. And the chain rule says I got to multiply by the derivative of that, which is negative 1, plus the second times the derivative of the first. Okay? And then, all right, what do we do with this e to the negative x? Well, that's e to the x on the bottom. And then they both have a common denominator, so we can bring them together. You might, if you're not careful, you might forget to do the chain rule on the derivative of e to the negative x power. So watch out for that. Question? Comment? Oh, can we do number 25? Sure. I didn't see your question until now, Maria. Let me just keep going here on examples. We'll get to that. Okay. Number 86. Natural log of 2x squared plus 3. Well, what do you do with a natural log? 1 over that thing, and then use the chain rule. And that's exactly what I did. So 1 over that thing you're taking the natural log of, 2x squared plus 3, times the derivative of 2x squared plus 3, which is 4x. So that one, not very difficult, but got to remember how to do the derivative of a natural log. (91) So here we go, the natural log again. So how do you take 1 over a fraction? I'm gonna wait for you guys to answer that one. How do you take, because it's the natural log of this thing, how do you do 1 over x squared plus 1?
Reciprocal.
Yeah, just take the reciprocal. So here we did it. 1 over that is x squared plus 1 over x. Do we have a chain rule? Oh yeah, we got a quotient, in fact. So denominator times derivative of numerator minus numerator times derivative of denominator over denominator squared. Okay, simplification. So on top, multiply by, just didn't do much in that line. And then you can do a little bit of canceling here. You got this x squared plus 1, and you got 2 of them down here. come up with your simplified answer. So I wanted to show you an example of what happens when you take the derivative of the natural log of a fraction. 1 over that, like Travis said, is just reciprocal of that. (93). Okay, so here, in general, we have a fraction. So on the outer, we got to do the quotient rule. Okay, so here we go with the quotient rule. Denominator times derivative of numerator. Oh, the derivative of the natural log of t is 1 over t minus numerator times derivative of denominator over denominator squared. What's t squared times 1 over t? Whoop, sorry. What's t squared? Yeah, you know, the t's cancel, you just get t, right? T. And then, yeah, you might simplify it by factoring a t out. You don't have to. If you do, the t's, you can get a little bit of a t simplification. T cancels with t to the 4th to give you t cubed on the bottom. Question or comment on 93? Let's do number 129. So the sine of x squared. So the outer function is the sine. So we're going to start by the derivative of the sine, of course, is the cosine. Cosine of x squared. And then we have a chain rule. X squared, the derivative is 2x. So just rewriting that. Oh, and this asks us to take, okay, so the first derivative ends up at 2x cosine x squared. So that's the first derivative. Number 129 asks you to find also the second derivative. Okay, so now we need to use what? The product rule. So the first, 2x, times the derivative of the second, minus sine of x squared. Chain rule, 2x, plus the second, times the derivative of the first. You know, 2x times 2x is 4 negative, you know, it's 4x squared, and then you multiply by a negative, so it becomes a negative. So that would be the second derivative, and you really can't combine these, so that's about as good as you can do there. Question or comment? Okay, I'm going to go to Maria's number 25 now. By golly, I don't have 25 done either. Okay, let's take a look at 25. Okay, first I got to find it. So it's x times the square root times the square root of 1 minus x squared. Okay. I'm going to get that changed color, and let's make this thing a little bit thicker. Okay, so f of x equals x times the square root of 1 minus x squared. So we would rewrite that, right? X times 1 minus x squared to the 1/2 power. So now we're set to do the derivative, and we need to, on the outside, we need to do what? Do the product rule. So the first times the derivative of the second. Plus the second times the derivative of the first. So, sorry, I wrote that on 2 lines, but I'm trying to manage space with you guys. So now, let's rewrite that. So what's, yeah. So we've got x times 1/2 times negative 2x. So x times negative 2x is negative 2x squared. Divided by 2 is negative x squared, right? And then that's over the square root of 1 minus x squared. And then we've got a square root on the top because it's to the positive 1/2 power. Now, I would simplify that, and I'm guessing the book would too. I would, let me grab blue here. So what I would do is I would multiply this top and bottom by the square root of 1 minus x squared, so I get a common denominator. And that gives me a common denominator. And what is that on the top? When you take a square root times itself, you get that thing without the square root. So that's 1 minus x squared plus a negative x, so it's 1 minus 2x squared. And that looks like where I would stop on number 25. Question or comments? So I hope we've made you more comfortable with the chain rule. You can't always do this 2-day thing, but I'm glad we did on this. This is so important. A major milestone in derivatives. Well, right about at the end, any further questions or comments? Okay, well, thank you. Good to have you 3 on board. I appreciate that.
Thank you.
You're welcome. Have a good one.